Okay, so you should have learned at this point that we have two types of regulators. We got all the regulators that we looked at prior to this lesson. Were all linear. In other words, however the input looked, it was providing a linear output. Okay. We also have another type, which is the switching regulator. And some of the advantages of the switching regulator is the fact that it's a little bit more efficient, right? It basically has higher efficiency, and it has higher regulator power handling capabilities. Okay, and the idea behind why it's more efficient is because our power switch, or basically, remember this is Q1, right? And the setup is very much like the pass transistor, with the exception that Q1 is never in its active region, right? Remember in an active region, it's a variable resistor, so it's increasing and decreasing current based on variable resistors. The way the power switch, and it's appropriately named the power switch, is because Q1 is basically either on, fully saturated, or off, fully cut off. Okay? So that's how he's behaving, and we're going to talk about this. What we have over here, so as far as how's the output being sensed, it's sensed through a comparator circuit. So all we have is a comparator circuit, and it senses it on the inverted input. So whatever the voltage potential is here, so we set a reference voltage here, and if obviously when we talked about comparators, if this potential is greater, right, the output will be low. If this potential is greater, the output will be high. Okay, so it's that simple. So you can see that based on what the voltage is doing, it could either, it'll go low if it's high on the output, or it'll go high if it's low on the output. Okay, and it goes into a gated latch. Now, one thing to note about the gated latch, it's basically comparing the two. Okay. We'll talk about the gated latch a little bit more. I've got another little diagram, and I'm going to show you basically some of the conditions that are required for the gated latch to put out. So what you need to know about the gated latch is it's putting out, based on what it sees, it's comparing this voltage here, which we're going to call the error, because this is an error detection circuit, and then the oscillator voltage. Okay, so this guy is putting in a constant oscillator, and we're going to see how he does that in the next slide. So what you need to know is he's basically putting out a square wave to the base of Q1. Okay, and Q1 is basically going to be, you can see based on this criteria, it's either going to be, if it's low, it's going to be off. If it's high, fully saturated. Oops. All right, full IL. Okay. Now, as far as this, we have a filter clipper circuit here. And what this is basically going to do is going to fine tune the input and output, right? The capacitor is going to be used to change or oppose any changes in voltage, right? So that's what capacitors basically do. And therefore, it's going to keep the voltage on the output fairly regulated. The inductor is going to oppose any changes in current, right? And it's going to keep the current relatively constant, while the diode is basically just used to clip the counter EMF, right, from the rectangle. In other words, it basically provides transient protection. Okay, but they're not, as far as what this circuit is doing, it's basically fine tuning the output. Okay, so as you can see, based on this criteria, this is how it's set up. Now we're going to go into a little bit more detail as to what's going on here with this next little diagram. So what you need to know about that gated latch now, let's look at this gated latch. It's basically a circuit. So if the oscillator, so the gated latch is comparing, like I said before, is comparing the error potential or the error voltage with the oscillator. So what you need to know is that it will produce a high whenever the voltage on the oscillator VO is greater than or equal to V error through the error voltage. Okay, so we saw that this is basically a comparator circuit, and this side here was tied to our voltage divider, right? And this side was our reference voltage. So V reference, right? And this one was tied to a voltage divider, okay? So what you also need to know about the oscillator is it's producing a triangular wave, okay? So it's kind of an oscillator and an integrator at the same time, okay? And that's simple. It's just all we do is we grab a sine wave, change it to a square wave, and then put it through an integrator, and then voila, we have a sawtooth wave. So it's grabbing these inputs. So you can see that as things change, so let's go with the scenario, for instance, that if, say, our load voltage increased. Our load voltage increased, that means this input, when compared to this one, is larger or more positive, meaning the error voltage goes down. V error goes down. Okay? If V error goes down, we end up with this scenario. Okay? Now, this is what's going on inside the gate, the gated latch. Now, the gated latch, all it does is produce an output, right? And one thing to note is that this configuration and the way the gated latch works is called pulse width modulation, right? And pulse width modulation basically means we're adjusting the width of the square wave. Notice that when we're looking at the adjustments, it's adjusting the width without adjusting the period. Notice the period is going to be identical. So all it's doing is adjusting the width of time on versus time off. In other words, the duty cycle, without actually changing the period. I mean, in other words, the time from positive going transition to positive going transition, it will be the same. Okay? So, again, we got scenario 1, it increased, we provide a low, and what this does, that low voltage is, that increase in voltage provided us with a low here, right? So in this scenario, what we have is voltage low, okay? We're down here. And what the output's going to look like when it's comparing, it basically grabs the two waves and produces an output, square wave, that matches that. And you can see here what we have is our time on will increase, okay? So with error voltage up, time on will increase, and this will affect the biasing on how much time we are saturated versus cut off. So and vice versa, if things were to flip around, right, and the potential against the reference would go up, right, so the reference would be larger, and this would affect our reference to our voltage, and it would modify the pulse width. In other words, change how much time we're on versus off, all adjusting that Q1 power switch to compensate for, again, when we need more current because voltage went down, or we need more voltage because or we need less current when voltage goes up, etc. Always the same idea, right? We're trying to maintain this relationship of V equals IR, okay? But we're doing it far more efficiently in the sense that we're not biasing Q1 on all the time. Sometimes he's literally off, okay, making it more efficient. This falls along the same lines as why are Class A B amplifiers, or like Class B amplifiers, more efficient than Class A as well. It's because we're not putting the transistors on as much. And this also increases how much power we can ultimately handle.